Sometimes it is necessary to modify the limits of your axes. You can do this for both of your axes, and it's actually very easy. We have the functions xlim and ylim. Both of these functions take a vector as an argument. So if I open brackets, you can see here it says limits, and we can simply create an empty vector that needs two values. Now I'm going to comment it, run the code, and you can see that our maximum value, our endpoint on our graph is crossing at x equals 20, voltage equals to 20, and current equals to 2. So we can make our x limit from 0 to 21, and we can make our y limit from 0 to, let's say, 2.5. And now when we run our graph, we can clearly see the graph itself. There is no ambiguity here. While with the previous way, someone could say, yeah, okay, but your graph reaches the end of your plot and we can't know if it continues there. It's really not visible. So this is a better way. Maybe 2.5 was a bit more, so let's use 2.2. Yes, I would say that this is a bit better. Maybe even... Yes, this is definitely better. Alright, what else can you do with the limits? Instead of hard coding these values, you can extract them. So you can say xlim minimum, and you can say 0, this is the one that we used, xlim maximum equals to 21. We can do the same thing for the y limit, so ylim min equals to 0 and ylim max equals to 2.2. Now, instead of using magical numbers here, we can use these variables. So here we can say xlim min, xlim max, ylim max, and ylim min. If we run it, we get the exact same result. Now, since we have extracted these values, we can modify them as much as we want. We could do it directly inside the function here, but that is not very clear what exactly is going on. So here instead we can do the following. We can say take the maximum value of our voltage, so y, and increase our x limit by 10%. So we are going to add 10% of our maximum value to the limit. So maximum plus max of u times 0.1. So when we multiply max of u by 0.1, we will get 10% of that. Let's do the same thing for the, let's see if it's working. Let's run it, and we get an x limit of 22. We can do the same thing for our y. So we can say max of I plus max of I times 10%, and if we run it, we get the exact same result as we had previously, but now if we change our values, our limits will change along with our values. So if I change the resistance to another resistance, we will get totally different results, but our graph stays the same. As you can see now, our maximum current is 1, not 2, and our y limit is clearly 1.1. So the limits of the graph are automatically corrected for our new values. Now, we can do the same thing for the minimum values, so that we can also automatically generate our minimum limits. To do this, we are going to use the following calculation. We are going to say, find the minimum value of our x limit, find the minimum value, which is minimum of u, and subtract from it 10% of our maximum value. So that way we will have the same excess boundaries on both sides. So we are saying minus the maximum of y times 0.1. And let's do the same thing for the y limit. So minimum of y, minimum of I, minus the minimum of I times 0.1 of maximum. Run it, and you can clearly see that we have the exact same boundaries, extended boundaries on all sides of our graph. Now, why is this helpful? This is helpful because if I now change my voltage from minus 10 to 20, we get a lot more values, but you can see that now our graph was our graph limits were correctly recalculated, and now our minimum axis starts from -10, and we have a little bit of excess to the left of the -10, and the same goes on the other side of our graph. The same goes for the y limits as well. That way, all of our limits are automatically recalculated for any size of graphs.